Hello everyone, welcome to my presentation. I am Amin and I am a former student at Technical University of Munich, and today I want to talk about multipolar. So the motivation behind our work is the following. In industrial assembly, robots are often required to solve a variety of relevant tasks with different dynamics. As a concrete example, here you can see the videos of two robots that are trying to solve the same peg insertion task. Although these two robots are solving the same task, they have different environmental dynamics. So here environmental dynamics means, for example, the length of their peg is different and also the diameter of their peg is different. So say that we have a good policy for the robot on the left side. Since the dynamics of the robot on the right side is not the same, we cannot just simply deploy the policy on the right side and expect it to work. So what we are interested here is to transfer the information from the policy of the robot on the left side to the robot on the right side such that it can learn to solve the task quickly, comparing to the case of learning from scratch. So in our problem setting, we assume that there exist multiple source environments and a single target environment instance. So these instances, they are basically the same environment. So they have the same state action spaces and reward functions, but they are different in state transition dynamics. So basically, given a state, an action, the next state would be different for each of these environment instances. So we assume that in this scenario, we have access to only the black box source policies. So for each of these source instances, there exists a policy, and we don't know the performance of this source policy. We don't know if this source policy is a neural network or a handcrafted policy. We only have access to the deterministic actions of these policies that are basically obtained from these source instances. And we also don't know anything about the source environment and the target environment. So for example, we don't know the dynamic parameter. So our novel problem settings poses some new challenges which makes many of the existing relevant works inapplicable. For example, because we have different state transition dynamics between the source environment and target environment, the option frameworks and policy reuse approaches will not work in this setup. And since we have access only to the black box source policies, basically the actions of these policies, we cannot do fine-tuning of the weights of neural network. And since we don't have any prior knowledge about the source environment dynamics, we cannot use much of the existing transfer reinforcement learning methods because they usually condition on the environment dynamics, which is not available here. And also about meta reinforcement learning approaches, they usually assume an access to a meta train set, which is not available here. So to solve this problem, we propose a new approach called multipolar. The way multipolar works is that given state S at time step t, we feed this state to our library of source policy and we get their actions, which here is denoted by AT. Then what we will do is essentially we adaptively aggregate the actions of the source policy with theta ag. So theta ag basically scales each action of each source policy independently. So we multiply theta ag to AT and we sum them. So we are basically learning a weighted average of the actions AT. I should emphasize that theta ag is neither normalized nor regularized and can scale each action of each policy completely independently, which means that we flexibly emphasize informative source actions while suppressing irrelevant ones. Then we also in parallel feed the states to the auxiliary network, here denoted by theta ag. And this auxiliary network can be anything like a multi-layer perceptron or any other function, as long as it is parameterized and differentiable. And then we add these two representations together and get a new representation, which serves as the mean of a Gaussian distribution in the case of continuous action space and the mean of categorical distribution in case of discrete action space. So what is happening here is that we have an adaptive aggregation of the the actions of the source policy, which basically gives us a baseline action that can introduce a strong inductive bias in the training of the target policy, even without knowing each source policy environment dynamics. And we have a residual part. So the residual part has two benefits. If the baseline action is good enough, then the residual policy can basically correct the aggregated actions for some unseen, for example, states. And if the aggregated actions is not useful, then basically the baseline action can help. Then basically the baseline action can help in the exploration process. So what will happen is that the auxiliary network will learn to do the task, and the baseline action basically just helps it to do a better exploration. So the advantage of the multipolar is that it can work with completely black box policies without accessing any information from the source environment dynamics. So it doesn't need to know the dynamics of the source environment. And it also doesn't need to know the original task performance. So this source policy might not be good, but this is totally fine because our theta ag is completely flexible and we'll learn to suppress the bad policies. And our experiment actually showed that this will happen. And our approach is applicable to both continuous and discrete action spaces. For our experimental evaluation, we selected 6 environments, which you can see here, and these environments cover both continuous and discrete action spaces. So, for example, here you can see the source environments for the RoboSchool ant environment. So here you can see the 4 ants that are working. And for example, here you can see that the policy of the ants on the right side are not very well, but on the left side, they seem to be well. And also you can see how diverse the dynamics of the environments are. So here the ants have really different designs. And here is the results. So on the left side, you can see the learning from scratch policy, which learns from scratch. And on the right side, you can see multipolar, which basically uses 4 source policy. And the multipolar is working quite well. And the same also happens in the in the case of Hopper. So for the sake of time, I didn't show the source environments. So you can see here that the multipolar is working much better than the learning from scratch. So for our quantitative evaluation, we did the following. For each of these 6 environments, we generated 100 instances with unique dynamics. Then we selected 3 random sets of size 4, which serves as environment instances for source policies of multipolar. So here we have 4 source policies for multipolar. If it was 8, for example, we would have had 3 random sets of size 8 and not 4. So then we trained multipolar on the target environment instances with 3 different random seeds. So overall, we will have 3 multiplied by 3 multiplied by 100 sessions for each of the 6 environments. We intentionally did this large number of experiments to make sure that good results are not by chance and they are representative of better performance. As baseline, we had 3 approaches. One was multi-layer perceptron, same as the auxiliary network, and which was learned from scratch, so without any prior knowledge or anything. And then we had an extension of the residual policy learning, which was a relevant work that was only working for a continuous action space. We extended that for a discrete action space, and we also made it adaptive to improve its performance. And also A2T approach, which we made some changes to make sure that it works for our setup. And as a metric, we had average episodic reward over training samples, and we used the bootstrap mean and 95% confidence bounds to again make sure that the results are significant or not. So first I start by showing you the learning curves. So here you can see that for RoboSchool Hopper, for example, our multipolar is much more basically faster in terms of learning speed comparing to the baseline approach. The same also goes for RoboSchool Ant, which basically shows our multipolar converges faster, and I should mention that these results are averaged over the number of experiments that I talked about in the previous slide. And here you can see the average episodic reward, and you can see that multipolar with for source policy achieves a mean of average episodic reward about 3 times higher than multi-layer perceptron, which is training from scratch, and about 2 times higher than A2T and RPL, which is really a astonishing result. And also in RoboSchool Ant, multipolar achieves a very good performance. So we did some further analysis. We first did an ablation study to make sure that both components of multipolar are necessary. So our first degradation version of multipolar was what we are showing on the plot on the left side. So what we did was that in order to make sure that this adaptive aggregation is really necessary, we froze all the weights to be 1. And we train multipolar in the same fashion as before. So basically, this uniform aggregation weights that you can see with orange color means that we are just simply averaging the source policy's actions, and we are basically learning to predict residuals around that. And you can see that this basically reduces the performance. And as another study, we basically use the same aggregation as multipolar, but we replaced the auxiliary network with some adaptive placeholder, which basically means that we wanted to know if we can learn to perform well with just a linear combination of the source policy. So just multiplying the adaptive weights and adding a bias to the actions, and that bias was state independent. And as you can see, this also did not perform well at all. And this shows that both components of adaptive aggregation and auxiliary network are necessary for multipolar performance. And on the right side, you can see the effect of number of source policies. So if we increase the number of source policy as expected, we get better results, but the gain seems to become smaller. Unfortunately, due to computational problems, we could not go more than a case equal to 16. As another study, we wanted to know the effect of source policy performance on the multipolar. If you remember, our source policies were basically, the performance were random, so we didn't know how good they were. And with a random performing source policy, we achieved the average episodic reward of 283. So if we change our sampling and we always select our set of source policy with high performing source policy, and I should emphasize that this high performing means in their own environment, multipolar performs very well, and the performance almost doubles. But the good thing is that if we have 4 low performing source policies, so source policies that are performing poorly in their own environment, the performance is as good as learning from scratch. And this means that the negative transfer does not happen with multipolar. So multipolar, and as you can see on the left side, so on the left side, we have an experiment which basically has two good policy and two low performing policy, and multipolar successfully learns to suppress the policies that are low performing and basically emphasizes the policies that are better. And this clearly shows that negative transfer does not happen in multipolar, which is a very good feature, and many of the transfer reinforcement learning approaches lack this property. So in summary, I introduced you to multipolar, which is able to work on black box source policies and is able to work in both continuous and discrete action spaces. I showed some of the results of multipolar in gym environments. If you are interested, I refer you to the paper for more results and more analysis. Our code is available on GitHub, and the Omron Synic X company is constantly looking for new interns. If you are interested, please send your CV. And thank you very much for your attention. I hope to see you in the virtual poster session.